Okay, next we discuss on the current voltage characteristic of the EMOSFET. So the characteristic of EMOSFET, we have two characteristics. The first characteristic is called a drain characteristic. So drain characteristic is we vary the VDS voltage and we measure the drain voltage at certain fixed gate voltage. Okay, for clear view, okay, let's redraw the structure here. This is gate, this is source, and this is drain. So actually we are yeah, this is VDS here. VDS here, the application of voltage across the drain and source, and VG here is VGS here is the application of the voltage from the gate, to the gate with respect to the source. So this is VGS here. So you see here, at the low VGS, so the current of the drain current will increase linearly. So this is this is a linear region. So this is a linear region where the drain current increase linearly as a VDS increase. So this is linear region. So, but when the VDS reach the what we call a saturation point or pinch off condition. So when VDS is equal to VGS minus the VTH, so the pinch off occurs and the current to start to saturate. So the current start to saturate. So this region called the saturation region. Okay, there is another region, we call it a cut-off region. The cut-off region is where there is no current flow. Okay, so when the ID is 0, this is called the cut-off region. Cut-off region occurs when the gate voltage is lower than the threshold voltage. So you can relate with the output characteristic of the BJT. Output characteristic of BJT has three operating region. We call it saturation, active, and cut-off. So the same with the BJT, cut-off region is where the current is 0. But the difference between the BJT and MOSFET is the naming of the region. In the MOSFET, we call the region where the current increase linearly with the VDS is called a linear region. But in the BJT, we call a saturation region. And then we see here the region where the current fixed at a certain value. For MOSFET, we call it saturation region. But for the BJT, we call it active region. So this is the difference between the naming of the operating region. So another IV or current voltage characteristic of the EMOSFET is called transfer characteristic. Okay, so transfer characteristic is simply the output versus input characteristic. So the output of the transistor in general is the ID, the drain current, and the input of the transistor is the control signal, which is a gate voltage, the VGS. So this is ID versus VGS. So ID versus VGS will have a characteristic that quite similar to the diode characteristic. So we have the threshold voltage here. VGSTH or VTH. Below the threshold voltage, the current is 0. Above the threshold voltage, the current will start to increase. So the increase of the current uh, is not in a linear fashion, but is more the rapid increment. So okay. So in this slide, it's showing the two transfer characteristics. What is the difference? The difference is the type of the EMOSFET. So until now, I have only discussed, or I only have explained on the N-channel EMOSFET. This is the N-channel EMOSFET. The N-channel EMOSFET is the MOSFET that induce the electron channel. So MOSFET that induce the electron channel. So the N-channel MOSFET use the P-type substrate. But on the other hand, the P-channel MOSFET is where we need to induce the whole channel. We need to induce the whole channel. And the substrate is N-type substrate. Because we want to induce the whole channel, the whole is positive charge particle, so we need to apply a negative gate voltage. So that's why the characteristic of the P-channel EMOSFET, which looks like this, the VGS is a negative value. So when the gate voltage is applied more negative, so we can induce more hole, so more current flow. Okay. We will use mostly the N-channel EMOSFET. Okay. So as explained in the previous slide, the drain current is 0 when VGS is 0, and then the drain current is 0 until the VGS reach the threshold voltage. Okay. Above the threshold voltage, the drain current can be expressed by this equation. ID equal to K VGS minus VGSTH square. What is K? K is actually a constant that related to the device parameter, device physical parameter. So the K usually given by the manufacturer, or if you have the characteristic, the transfer characteristic, the K can be calculated by using the value in the graph. So K is equal to ID on over VGS minus VTH square. So this is taken from the first equation. So what is ID on? What is the VGS? This is VGS. It's actually VGS on. So ID on and VGS on is any point. You can take this point, you can take this point, any point at the on condition, where so the current can start flow. So let's put this one. This will be your VGS on, and this will be your ID on. So in summary, the mathematical expression for the ID can be written as this. ID is 0 when VGS is less than VGSTH. If VGS ID will equal to K VGS minus VGS TH, when the VGS is larger than VGS TH. So this is the example. The slide show if you are given a k constant. So actually you can plot the transfer characteristic of a EMOSFET. For example, the k is given as 0.5 times 10 power of minus 3. The unit for the k is ampere, voltage, power of minus 2. So and then it's also given that the threshold voltage. So you see here, we use in this example use the different symbol. Vt is 4 volt. So this is actually the threshold voltage. So you can draw the graph. So this is below than Vt, Id is 0. Okay, because of below than the threshold voltage. Above the threshold voltage, you apply the this k VGS minus Vt square. So you just put the k value here, and for example, this is VGS here is 5. So 5 minus the threshold voltage is 4. So you get here 1 square times 0.5. So you'll get the ID 0.5 milliampere. So it will be this, the point. You can plot the point. So you can continue calculating the point. They say for the 6 VGS equal to 6 volt, 7 volt, and 8 volt. For example, for the 8 volt, so we'll get the 8 milliampere. So when you have this point, you can connect all this point and you can obtain the transfer curve. Okay, this is another situation. Let's say you are given the transfer characteristic and you need to find the related parameter. So this is the transfer characteristic of a transistor. So the current is quite large. So I'm not sure about what is the structure of the capacitor, but this is the EMOSFET. Okay, and then we have the two curve here. One is the curve at the high temperature, 150 degrees Celsius. One is at the room temperature. So let's consider the room temperature transfer curve. So find the threshold voltage. So the threshold voltage will be somewhere along, this is along 2.5. So the threshold voltage will be 2.5 volt. Okay. So how about the K? So the K is you can calculate the K from the ID equal to K VGS minus VT square. So K is ID on over VGS on minus VT square. So we can use this point. So at this point, the VGS on is 3 volt and ID on is 2 ampere. So this is a 2 over 3 minus 2.5 square. So you will get the K is equal to 2 divided by, so we have this 8. So the unit for K is 8 over V square. So this is if you're given a transfer characteristic and you need to find the threshold voltage and the K value, K constant. Okay, so next is the symbol of the MOSFET. So we know that the MOSFET has a 3 terminal, gate, drain, and the source. Gate, drain, and the source. And then we have to know that the MOSFET has an N channel and P channel. So basically the MOSFET symbol will have the similar symbol of the capacitor. So this is the capacitor between drain and gate and the drain. We have the capacitor symbol here. This is capacitor. But here, because this is the EMOSFET, so this line will be dashed line. So the dashed line means that the normally condition, there is no connection between drain and the source, because there is no uh, channel, physical channel. So you need to induce the channel to connect between source and the drain. So that's why we have the dashed line here. Okay, and then how to distinguish between the N channel and P channel is by see the arrow direction. The arrow that pointing in is the N channel, pointing out is the P channel. And then this arrow is actually the substrate electrode or substrate connection, but the substrate connection will we ignore. We will not go into the detail of the substrate connection. We try to simplify how we deliver this course. So we just ignore this substrate connection. So, and then how we can distinguish between drain and the source. The source is where we have this connection with the substrate.